What are depth rocks? Depth rocks, often referred to in geological contexts, are types of rock formations that originate from considerable depths within the Earth's crust. These rocks form under extreme conditions of high pressure and temperature, typically several kilometers below the Earth's surface. Their formation is a result of various geological processes, including magmatic activity, metamorphism, and tectonic movements. One of the primary categories of depth rocks is igneous rocks, particularly intrusive or plutonic rocks. These rocks form when magma cools and solidifies beneath the Earth's surface. Due to the slow cooling process, intrusive rocks, such as granite, diorite, and gabbro, tend to have large, well-formed crystals. The depth at which these rocks form allows for the growth of these sizable mineral grains, giving the rocks a coarse-grained texture. Metamorphic rocks are another significant type of depth rock. They form when existing rocks, igneous, sedimentary, or other metamorphic rocks, undergo physical and chemical changes due to intense pressure and temperature conditions, usually deep within the Earth's crust. Common examples of metamorphic rocks include schist, gneiss, and marble. The depth and intensity of the metamorphic processes contribute to the distinct banding and foliation patterns often seen in these rocks. The study of depth rocks provides valuable insights into the Earth's internal processes and the history of its geological evolution. For instance, the composition and structure of depth rocks can reveal information about past tectonic activities, the formation of mountain ranges, and the conditions of the Earth's interior at different geological periods. Geologists often study these rocks through various methods, including field observations, petrographic analysis, and geochemical assays, to understand better the dynamic processes shaping our planet. Moreover, depth rocks have practical significance. Many of them contain valuable minerals and resources, such as precious metals, gemstones, and industrial minerals. Understanding their formation and distribution helps in mining and resource extraction industries, contributing to economic development. In summary, depth rocks are integral to our understanding of Earth's geological framework. They form under extreme conditions deep within the crust, resulting in distinctive features and compositions that provide crucial information about the planet's inner workings and history. Their study not only advances scientific knowledge but also supports practical applications in various industries. Formation of depth rocks. The formation of depth rocks is a complex and multifaceted process that occurs under the intense pressures and high temperatures found deep within the Earth's crust. This process can be categorized into three main types: igneous, metamorphic, and, to a lesser extent, sedimentary processes, each contributing to the formation of different types of depth rocks. 1. Igneous processes. Igneous depth rocks, particularly intrusive or plutonic rocks, form from the cooling and solidification of magma beneath the Earth's surface. These rocks originate from the molten material found in the Earth's mantle or lower crust. As magma slowly rises towards the surface, it may become trapped in large chambers where it cools gradually over millions of years. This slow cooling process allows crystals to grow large, resulting in the coarse-grained texture typical of plutonic rocks. Examples: granite, composed primarily of quartz, feldspar, and mica. Granite forms deep within continental crust and is known for its durability and widespread use in construction. Diorite, consisting of plagioclase feldspar and ferromagnesian minerals, diorite typically forms in volcanic arcs. Gabbro, rich in pyroxene and plagioclase, gabbro forms from mafic magma and is commonly found in oceanic crust. 2. Metamorphic processes. Metamorphic depth rocks form from the transformation of existing rocks under conditions of extreme pressure and temperature, typically several kilometers below the Earth's surface. This process, known as metamorphism, alters the mineral composition and structure of the original rock, protolith, without melting it. Types of metamorphism. Regional metamorphism occurs over large areas, usually associated with mountain-building events, orogeny, where tectonic plates collide. The intense pressure and heat generated during these events cause widespread metamorphic changes. Contact metamorphism happens when rocks are heated by nearby magma intrusions, affecting a smaller area but resulting in significant mineralogical changes. Examples: schist, characterized by pronounced foliation and formed under medium to high-grade metamorphic conditions. It often contains mica, quartz, and garnet. Gneiss displays distinct banding due to the segregation of mineral types and forms under high-grade metamorphic conditions, typically derived from granite or sedimentary rock precursors. Marble, formed from the metamorphism of limestone, marble is primarily composed of recrystallized calcite or dolomite. 3. Sedimentary processes, at depth. While sedimentary rocks typically form at the Earth's surface, some sedimentary processes occur at considerable depths. These processes involve the burial, compaction, and lithification of sediments that have been transported and deposited over long periods. Over time, as these sediments are buried deeper, they undergo diagenesis, transforming into solid rock under the pressure and temperature conditions found at depth. Examples: shale, formed from clay-sized particles that settle in calm water environments and, with increased depth and pressure, can transform into slate through low-grade metamorphism. Sandstone, composed of sand-sized particles that are compacted and cemented together. Deep burial can increase its hardness and density. Geological significance. The formation of depth rocks provides invaluable information about Earth's geodynamic processes. The study of these rocks allows geologists to reconstruct past tectonic events, understand the conditions of the Earth's interior, and trace the history of crustal evolution. For example, plate tectonics, depth rocks like gabbro and basalt in ophiolites, sections of oceanic crust and upper mantle, help to elucidate the processes of seafloor spreading and subduction. Mountain building, regional metamorphic rocks such as schist and gneiss reveal the intense pressures and temperatures involved in the formation of mountain ranges. Mineral deposits, many depth rocks host valuable mineral deposits, including ores of metals like gold, copper, and platinum, making their study crucial for resource extraction industries. Practical applications. Understanding the formation and characteristics of depth rocks has numerous practical applications. Construction, durable and aesthetically pleasing depth rocks like granite and marble are extensively used in building and architectural projects. Mining, depth rocks are often rich in economically valuable minerals and ores, guiding exploration and extraction efforts. Geothermal energy. Knowledge of subsurface rock formations is essential for locating and exploiting geothermal energy resources. In summary, the formation of depth rocks involves intricate geological processes that occur under the Earth's surface. These processes produce a diverse array of rock types, each with unique characteristics and significant geological, economic, and practical implications. Studying these rocks provides critical insights into the Earth's interior and its dynamic history, advancing both scientific understanding and practical applications. Properties of depth rocks. Depth rocks, formed under the extreme pressures and high temperatures found deep within the Earth's crust, exhibit a range of distinctive properties that reflect the unique conditions of their formation. These properties include mineral composition, texture, structural features, and physical characteristics, all of which are crucial for understanding their geological significance and practical applications. Mineral composition. The mineral composition of depth rocks is primarily determined by the types of minerals that crystallize from magma or recrystallize during metamorphism. The composition can vary significantly based on the source material and the specific conditions of formation. Examples: granite, composed mainly of quartz, feldspar, both plagioclase and orthoclase, and mica, biotite or muscovite. These minerals give granite its characteristic light color and speckled appearance. Gabbro, rich in pyroxene and plagioclase, often with minor amounts of olivine. This composition results in a dark, dense rock. Schist contains abundant mica, along with quartz and garnet, which give it a shiny, foliated appearance. Marble, predominantly composed of calcite or dolomite, resulting from the metamorphism of limestone or dolostone. Texture. The texture of depth rocks is a direct consequence of their formation environment. Texture refers to the size, shape, and arrangement of the minerals within the rock. Examples. Granite exhibits a coarse-grained, phaneritic texture due to the slow cooling of magma, which allows large crystals to form. Gneiss, characterized by a banded texture, where minerals are segregated into alternating light and dark bands, resulting from high-grade metamorphism. Schist displays a pronounced foliation, with minerals aligned in parallel layers, reflecting the directional pressure during metamorphism. Gabbro, like granite, it has a coarse-grained texture but is typically darker and denser. Structural features. Depth rocks often show distinctive structural features that provide insights into their formation and the geological processes they have undergone. Examples. Foliation, a planar arrangement of mineral grains or structural features within a rock, common in metamorphic rocks like schist and gneiss, indicating directional pressure during formation. Banding, seen in gneiss, this feature results from the segregation of different minerals into distinct layers, reflecting high-grade metamorphic conditions. Intrusions, igneous depth rocks like granite and diorite often form large intrusive bodies, plutons, such as batholiths, dikes, and sills, which can cut across existing rock layers. Physical properties. The physical properties of depth rocks, including density, hardness, and porosity, are influenced by their mineral composition and texture. These properties affect the rock's durability and suitability for various applications. Examples. Density. Depth rocks are generally denser than surface rocks due to the high pressures involved in their formation. For instance, gabbro and basalt are denser than granite due to their higher content of heavier minerals like pyroxene and olivine. Hardness. The mineral composition of depth rocks contributes to their overall hardness. Granite is hard and durable, making it suitable for construction and countertops, while marble, though less hard, is prized for its aesthetic qualities. Porosity. Most depth rocks have low porosity because the intense pressure during formation compacts the minerals tightly, leaving little space between grains. This makes them less permeable and more resistant to weathering and erosion. Geological significance. Depth rocks provide valuable information about the Earth's interior and tectonic processes. Their study helps geologists understand the formation and evolution of the Earth's crust and mantle. Examples. Tectonic history. The presence and distribution of certain depth rocks, such as gneiss and schist, can indicate past tectonic events, like continental collisions and mountain-building episodes. Magma evolution. The composition and texture of igneous depth rocks reveal the history of magma evolution, including processes like fractional crystallization and partial melting. Metamorphic conditions. The mineral assemblages and textures of metamorphic rocks provide clues about the temperature and pressure conditions during metamorphism, helping to reconstruct the geological history of a region. Practical applications. Understanding the properties of depth rocks has numerous practical applications in various industries. Construction. The strength and durability of depth rocks like granite and marble make them ideal for building materials, countertops, and monuments. Their aesthetic appeal also makes them popular in architectural design. Mining. Depth rocks often host valuable mineral deposits, including ores of metals like gold, copper, and platinum. Understanding their formation and distribution is crucial for efficient exploration and extraction. Geothermal energy. Knowledge of subsurface rock formations is essential for locating and exploiting geothermal energy resources, which rely on the heat stored in depth rocks. Environmental studies. The properties of depth rocks can influence groundwater flow and storage, making them important in hydrogeological studies and environmental assessments. Conclusion. Depth rocks, formed under extreme conditions deep within the Earth's crust, exhibit unique properties that reflect their complex formation processes. Their mineral composition, texture, structural features, and physical characteristics provide critical insights into the Earth's geological history and have numerous practical applications. Studying these rocks not only advances our understanding of the planet's interior and tectonic processes but also supports various industries, from construction and mining to energy and environmental management. Classification of depth rocks. The classification of depth rocks, which are primarily igneous and metamorphic rocks formed deep within the Earth's crust, is essential for understanding their formation processes, composition, and properties. This classification is based on various criteria including mineral composition, texture, and formation environment. Here is a detailed exploration of the classification of depth rocks. 1. Igneous depth rocks. Igneous depth rocks, also known as intrusive or plutonic rocks, form from the slow cooling and solidification of magma beneath the Earth's surface. This prolonged cooling allows for the development of large, well-formed crystals. Classification by mineral composition. Felsic rocks. Granite, composed predominantly of quartz, feldspar, both orthoclase and plagioclase, and mica, biotite or muscovite. Granite is typically light-colored and coarse-grained. Granodiorite contains more plagioclase than granite and has a composition between granite and diorite. It also contains quartz and biotite or hornblende. Intermediate rocks. Diorite, intermediate in composition between felsic and mafic rocks. Diorite contains plagioclase feldspar along with hornblende, biotite, and/or pyroxene. It is usually medium to dark in color. Mafic rocks. Gabbro, rich in pyroxene and plagioclase. Gabbro is darker and denser than felsic rocks. It may also contain olivine and is the intrusive equivalent of basalt. Ultramafic rocks. Peridotite, dominated by olivine and pyroxene. Peridotite is very dense and dark, often found in the Earth's mantle. It is the primary rock type of the mantle. Classification by texture. Phaneritic texture, coarse-grained texture where individual mineral grains are visible to the naked eye, as seen in granite and gabbro. Pegmatitic texture, extremely coarse-grained texture found in pegmatites, which are formed from the last stages of magma crystallization and can contain very large crystals. 2. Metamorphic depth rocks. Metamorphic depth rocks form from the alteration of existing rocks under high pressure and temperature conditions without melting. These rocks are classified based on their texture and mineralogical composition, which reflect the conditions of metamorphism. Classification by texture. Foliated metamorphic rocks. Slate, fine-grained and formed from low-grade metamorphism of shale. Slate exhibits a well-developed foliation known as slaty cleavage. Phyllite, slightly higher grade than slate. Phyllite has a sheen from fine-grained mica crystals and shows a wavy foliation. Schist, medium to high-grade metamorphic rock with pronounced foliation and larger mineral grains, often containing mica, garnet, and quartz. Gneiss, high-grade metamorphic rock with distinct banding of light and dark minerals, indicating intense metamorphism. Non-foliated metamorphic rocks. Marble, formed from the metamorphism of limestone or dolostone. Marble is primarily composed of recrystallized calcite or dolomite and lacks foliation. Quartzite, derived from quartz-rich sandstone. Quartzite is a hard, non-foliated rock formed through the recrystallization of quartz grains. Classification by metamorphic grade. Low-grade metamorphism produces rocks like slate and phyllite, where temperatures range from 200 degrees Celsius to 400 degrees Celsius and pressures are relatively low. Medium-grade metamorphism produces rocks like schist, formed under temperatures from 400 degrees Celsius to 600 degrees Celsius and moderate pressures. High-grade metamorphism produces rocks like gneiss and some high-grade schists, with temperatures exceeding 600 degrees Celsius and high pressures. 3. Hybrid and special depth rocks. Some depth rocks exhibit characteristics of both igneous and metamorphic processes or form under specific conditions that do not fit neatly into the above categories. Migmatite, a rock that has undergone partial melting, displaying both igneous and metamorphic features. Migmatites often have a mixed appearance with streaks of granite-like material within a foliated metamorphic matrix. Eclogite, a high-pressure metamorphic rock composed mainly of garnet and amphicite, a type of pyroxene, typically formed from basaltic material subducted into the mantle. Amphibolite, a metamorphic rock mainly composed of amphibole and plagioclase, formed under conditions of medium to high-grade metamorphism, often derived from basaltic precursors. Geological significance and applications. Understanding the classification of depth rocks is crucial for geologists as it provides insights into the tectonic processes, thermal history, and chemical evolution of the Earth's crust and mantle. The classification also has significant practical applications. Construction. Depth rocks like granite and marble are highly valued in the construction industry for their durability and aesthetic appeal. Mining. Certain depth rocks host valuable mineral deposits, making their classification essential for exploration and extraction. Geothermal energy. Knowledge of the distribution and properties of depth rocks helps in locating and exploiting geothermal resources. Petrology. The classification aids in understanding the genesis and evolution of rocks, contributing to broader geological models and theories. Conclusion. The classification of depth rocks involves an in-depth understanding of their mineral composition, texture, and formation processes. This classification helps in deciphering the geological history of an area, identifying economically valuable resources, and applying this knowledge to practical and scientific endeavors. Through detailed study and classification, depth rocks reveal the dynamic processes that shape our planet's interior and surface.